this present, how we got to where we are today. And this is driven in many ways by the progress in hardware. And this is one example graph which shows that if you plot the coherence time of superconducting qubits over years, it's really been doubling every period or so, sometimes called Shokop's law, because a lot of these points were driven by Robert Shokop's advances at Yale. But also because of another phenomenon, which is that not only has there been drive in the materials, but there's been drive from the commercial sector, with companies like Google and IBM and Microsoft really significantly investing in making these possible. I'm not going to talk about either of those directions. What I wish to share with you today is purely just about the math and the algorithms, the theory of what has happened. Because in concert with these two things happening has also been dramatic advances in understanding the theoretical needs and possibilities. So I will contradict what Umesh said. It's not just that the experimentalists are catching up with the theorists. It's that the theorists are catching up with reality. And that's the story I want most for you to understand. And in this story, I'll tell you three parts about the story of evolving time, about the story of turning from evolving time to becoming grounded in what real hardware can provide, but also looking at the ground of the truth of what chemists want, and then wrapping up with the shift from these kinds of high-flying theoretical thoughts to what might be reality. So let me start on all of this, but I am drawing very highly from these three references. I highly recommend, in particular, this one. It's a report on a National Science Foundation workshop. You can Google the title and find it, and I'll give you more references, return to these references later. This is a phenomenal roundup of all the quantum chemistry and quantum algorithms used in quantum simulations today. This is a beautiful article about quantum computational chemistry from 2018, the Oxford-led groups. And then a report from another subcommittee. This is from the Department of Energy about nuclear physics and quantum information science. So I'll draw from these three as the major sources. But I also give references to all the original works and reviews as I go along. Because what I'd like for you to do is to get a perspective over the field. But please also keep in mind it will be a bit of an opinionated perspective, because I also want to try to teach one small idea. Very, very beautiful idea to me as I go through these. So let's start with the very origin of quantum simulation. And this is the goal that everyone originally had, which is to simulate this differential equation, which we know. I knew I had to put complexity theory in, being at the Simons Institute. It is BQP complete, meaning that we can simulate any bounded error quantum polynomial time circuit using quantum simulation. That's simple to understand because you simply push this circuit into the Hamiltonian and evolve it forward. Now, the trick, however, is that this is far too complicated to simulate in general for any Hamiltonian. So very rapidly, focused attention was placed on Hamiltonians, which have some simplifying assumptions, such as they have sums of terms that often occur, for example, in lattices. And these terms are non-commuting, so it leads to something that is non-abelian, but they are importantly local, so that they could, in principle, be physically realized. And if you start with this simplifying assumption, you can use a very fundamental fact of mathematics known as the Lie product formula, or the Trotter-Suzuki formula in its higher order versions, which just says that the exponentiation of this, or the time evolution under some Hamiltonian, can be done by evolving under the pieces of that Hamiltonian, toggling them back and forth with small time steps, and then doing many of these sequences repeated. This is the very original result from Seth Lloyd in his science paper from 1996, and it has an extraordinary cost. The number of elementary steps goes something like n cubed, where n is the number of terms in the Hamiltonian that we are using for this approximation, and t is the simulation time that you desire, and epsilon is the simulation error. And at this point, it was considered a phenomenal, groundbreaking result, as quoted in the literature. But look at what has happened if you do something beyond this first order. So more recently, an order 2k expansion has shown that you can have a n squared t to the first level of complexity instead. And I won't say much more about this right now, but this is a result from 2019, which is already obsolete. That's how fast this field has been moving. More on this in a bit. So the key idea is approximations about what real physical system you want to simulate. And this is another approximation that led to a great deal of insight, namely the idea that Hamiltonians can be sparse. Drawing from Andrew Child's work, and he's one of the organizers of this whole workshop, for example, your Hamiltonian might look like this, a pattern of interconnectivity between nodes, drawn in here as a two-dimensional matrix. And if we then draw another idea, well known in mathematics and computer science, which is the notion of walks, we might try to walk on this graph of connectivity. Here's a circuit, and I'm going to show you this kind of a circuit several times, and I would like you to pay attention to them. You start with a qubit, you put it in superposition with a Hadamard operator, not to be confused with a Hamiltonian, and then if it's 1, you move right, and if it's 0, you move left. Or maybe you weight these with some probabilities. That is, you'll walk along the graph defined by h, and if you do so, repeat this in just the right way, you get a result, which is a wave function that has evolved by e to the minus I cosine inverse of h and t, which is really beautiful. You get Hamiltonian evolution with a little bit of a catch. That is, you got to have a cosine here, but if you expand this to first order, it's exactly what you're looking for, e to the minus I h t. And so this is one of the most important early steps in the whole field of quantum simulation, and it led to a remarkable advance in the number of elementary steps needed for quantum simulation. So it goes as tau, where tau is now the product of the sparsity of the Hamiltonian, the maximum eigenvalue of the Hamiltonian, and the simulation time that you desire, where epsilon, again, is the error that you desire. So notice it goes as log 1 over epsilon, not as 1 over epsilon anymore. And now we're starting to get something which is going as t instead of some higher order power. Okay. Now, at the same time as around this walk, maybe a few years later, came another idea, observing that many molecular Hamiltonians and other physical Hamiltonians are sums of unitary matrices when one reduces them to practice. And thus, it's also conceptually interesting to find a way to realize evolution which is described by a sum of unitaries. Now, this one, in computer science language, each one of these is an oracle, can be done with another quantum circuit. And it's remarkable to see this quantum circuit. It's, again, essentially a qubit controlling the evolution, tied to the controlled evolution of another physical system. This one I've drawn as a single wire, but it doesn't have to be a qubit. It can be a much larger system. But the essence is you have one qubit, and what's happening over here is that as it does something, remember I had a 0 controlled left, a 1 controlled right. Now it's going to be a 0 controlled UA and a 1 controlled UB. And if I rotate this by some superposition, which is between 0 and 1, then depending on that weight, it'll do a little more of this one and a little less of this one, or vice versa. And then with some probability, when you measure this, like with outcome 0, you get a weighted sum of these two unitaries. That's obvious from this interpretation. But another interpretation of what's going on is that these unitaries are kicking phases back into this qubit. And those phases are going to be very important, very subtly and interestingly important as I go through this talk. So with this idea and this method, now called the linear combination of unitaries approach to quantum simulation, Berry, Childs, Cleve, Kothari, and Roland Soma were able to get the same result that's obtained with the quantum walks. Now this is very nice, but around the same time, computer scientists also crunched through and found a lower bound. That instead, the best possible should be the sum of the time plus some error terms, not the product of the time and the error terms. So there's a gap. Now, let me step back a little bit and try to explain a little bit more about the dynamics of this qubit here, because I think that's very insightful, and also maybe even the most fundamental thing that's going on inside quantum simulation. And I'll submit later, it may also be the most fundamental thing going on in quantum algorithms altogether. So this is the idea known as composite pulses. much of which was done right here at Berkeley, Alex Pine's group. Suppose we have a rotation by angle theta about some axis phi, where phi is defined as an axis in the xy plane of the block sphere. So I've located right here. This is the normal qubit representation, where 0 is on the top and 1 is on the bottom. And for those of you who are mathematicians, this is an SU2 representation, which is locally isomorphic to SO3. And this rotation by angle phi is going to be a rotation around this red axis by some angle theta. And now, the remarkable thing is that if you apply this one rotation once, and I measure the probability of transitioning between 0 and 1, it's a very well-known function, just the Rabi oscillation, which peaks in the middle when I've got a 190-degree pulse. Now, if we apply 3 pulses and change the angle, I just randomly chose 0, 1.5, and 0, then you get a different probability map, which we might call a response function of sorts. It looks like this. It's no longer a Rabi oscillation, but it wobbles up in the middle. I was saying before this morning to some folks, this is kind of like a beam that's being formed in different ways. And I can use 5 pulses to make this flatter. I can also use 5 pulses to stick a hole in the middle. And I can use a sequence of pulses to get all sorts of functions, like ORs and majority functions, and maybe even a tanh or a ReLU if you're interested in those kinds of things. But the fundamental idea is the following, shown here. It is known, it's a fact. You can show easily that if you take a product of rotation operators of single qubits, and there are d of these, then the result is another SU2 matrix where in the upper left corner, actually all of these entries, but let's focus on the upper left corner, you got a polynomial of order d in cosine theta, or in theta if you wish. This is a result from Guanghao Loader and Ted Yoder. Guanghao is sitting in the audience. And you'll hear much more about his work in a bit. So the reverse of this is a remarkable thing. This is a theorem that says that if I start from a polynomial rather than starting from the phases, so this forward problem is easy, I just multiply. The reverse problem is not at all conceptually obvious to be solvable, but it turns out to be solvable. I can specify this polynomial, and as long as it satisfies a set of well-behaved criterion, then there will always exist a vector of these phases which you can choose so that you can realize a polynomial of your desire. Okay. And we know in physics and math that such kinds of inverse solutions are rare, and they speak loudly. This one turns out to draw significantly from a well-known set of theorems in discrete time signal processing, in particular an algorithm called the Ramez exchange algorithm. So let's take this for granted. What does this mean back for our top-level problem of quantum simulation? Why have I taken you on this journey? Well, if I encode this Hamiltonian as being part of some unitary, so I have these Pru2 projectors of a form such that, for example, H is encoded in the upper left block of that unitary. Remember, H itself doesn't have to be unitary, but it's embedded inside another unitary. And this is part of a construction that is called qubitization. And I won't explain that here, but you can look it up. It turns out, for example, that if the projector projects along a single state of this form, this is Grover's algorithm. But if you use the more general case and allow this to be any type of projector, you can do a projector which flips your qubit. Here's that physical system. It can be arbitrarily large. And if you project back onto the system and perform a z rotation about your axis phi here, this is a rotation operator of h, where h is the angle. You may think of it as each of the eigenvectors of h. But this is now just the construction I gave you a moment ago, so that we may use this quantum signal processing theorem and say that we can find a sequence of phases up here which will allow us to construct a desired polynomial function of h. And this allowed Guanghao Lo to build this beautiful construction of taking a quantum walk Hamiltonian. Remember from Andrew Child's work, it gives this inverse cosine of h as evolution. Think of that as a theta. Now, if you do cosine of this theta, that just gives you h back, and that thus gives you e to the minus iht to all orders without having to take a small h approximation. And this gave one of the first constructions for a complexity cost, which gives you a sum of the time and then the errors that matches exactly the lower bound that had been predicted. So this became the optimal quantum Hamiltonian simulation algorithm. And you can read about it in these references. Now, this is a long sought story, and many performance comparisons have pointed out the evolution of these techniques that have gone through using product formulas as I described, different series expansions, and then this qubitization and quantum signal processing. But I'm afraid actually all of this has become obsolete in a way due to another beautiful result that just came out a few weeks ago. This is a preprint from Andrew Child's group. Childs, Yansu, Tran, Nathan Weep, and Xutren Zhu, which have taken forth the trotterization technique that started the whole field off and much more carefully bounded all the errors and shown that as you make more approximations and know more about the structure of the physical Hamiltonian, so either electronic structure or K-local is the technique I was describing much earlier, then you get various costs. So qubitization and quantum signal processing gets something that when it's t and n to the k, and that's actually the same thing that you get with trotterization. But if you know more, you can do much better. Like in this case, with a certain kind of fall off in the domain size, then you get, like for lattices, you get n squared t to the first as opposed to qubitization scaling, and so forth. So the field is rapidly still moving. And I hope you can see from this that it is algorithms that have been catching up to what is possible fundamentally, rather than the hardware driving this. And it's a remarkable evolution. I actually believe that trotterization and quantum signal processing are fundamentally the same thing. And after all, trotterization is about single qubit dynamics. And so isn't that remarkable? As single qubit dynamics, the dynamics at SU2 are really driving all of these insights and developments. Okay. So let me move on from there. We've been talking about time evolution. Any questions before I move forward? Yes, please, in the back.
You mentioned the optimality of the tau plus the log over log log.
Yes.
What is it that's going wrong with the optimality result in these cases that you're talking about? I assume it's some sort of like assumption of the system being generic enough for the lower bound, but what kind of assumption is that?
Yeah, so you have to make assumptions to get the optimal lower bound, and typically those are that it's an oracular Hamiltonian, and you assume some kind of locality. The rest of these systems that I show here have different kinds of properties which have yet not been generically, in most generic cases, analyzed to see where the local bound is going to be. But you can actually understand one of those very easily. Thou shalt not be able to simulate a quantum system faster than time evolves forward. This is called the no fast forwarding theorem from God. And it says that you shouldn't be able to speed up time. But theoretically, computer scientists don't adhere to this, as I will say in a little bit. So there are a lot of interesting catches, and I'll mention some more of them. Another question? I thought there was a hand. Yes, please.
Where does the sparsity assumption come in the signal processing?
Where does the sparsity assumption come in the signal processing? Remember that in the way I described it, the signal processing stood on top of the walk formalism. And the walk used the sparsity of the graph that it was walking upon. It turns out that that is not necessary. There's another way to put a sparsity assumption into quantum signal processing and qubitization. But I will leave Andras Guillen to speak about that in a few days, because there are some beautiful constructions there. Other questions, please? Okay. Then hopefully you'll have more as I tell you about being grounded. The goal of chemistry calculations in quantum chemistry has often been electronic structure calculations, specifically to determine what happens in what is called low energy properties. And over here I show you a tree, sometimes called the tree of quantum chemistry or quantum theoretical chemistry, which shows how the roots of all the methods that are used today are based on expansions of the ground state density functional theory and versions which are built on coupled cluster theories. For example, why this is important is illustrated by this phase diagram of high temperature superconducting materials. Temperature can be equated with energy, and you can look at the low energy sector of this and see that there are remarkable variations in what one can get, all the way from Fermi liquids, D-type superconductivity, all the way over to different kinds of matter, essentially. And to answer this question is very difficult because the electrons are, we say, highly correlated. But that just means that there's this global extra property called fermion antisymmetrization that is needed because the electrons do not allow each other to sit on top of one place. And this leads to a global constraint that has complex properties. So if one wants to find the ground state and find the ground state's state and energy, there are some options. One of them that's very well known from the very early days is called adiabatic preparation. And it's pretty easy to understand. If you wish to prepare the ground state of some Hamiltonian, H, you can start by preparing a ground state of a different Hamiltonian, H naught, which you know and is very easy, such as the ground state of all spins in the uniform magnetic field is just the spins pointed in the low energy state, like aligned with the field if there's positive coefficient. So suppose we do that, and let this be like the energy, and I'll change a reaction coordinate in this direction. This reaction coordinate is the pseudo time s, which I'll introduce as a parameter to move between the starting Hamiltonian H0 and the final desired Hamiltonian H, which you would like to get a ground state of. And as you slowly change this parameter s from 0 to 1, so at 0 it starts with the easy Hamiltonian, at 1 is the desired Hamiltonian, it is well known that if you do this sufficiently slowly, you will get, having started from a ground state that you know, you will evolve into the ground state of a Hamiltonian you don't know the ground state of. The catch is, of course, that if you have a set of higher energy states like this one up here, if you evolve too fast, you might actually swap and move into an excited state. And so the time, the maximum rate that you can move is determined by this gap here, and your evolution time must be much less than 1 over the gap. This is a very simplified explanation. The actual adiabatic evolution formula is a little more complicated. But conceptually, this is a very easy to understand idea, and it does give you the ground states under these assumptions. But there's another thing you might want to get, which is not just the state, but it's ground state energy. And you might want to get some these states with some kind of precision. And so one moves from using just adiabatic state preparation to doing something a little more sophisticated. And this is where a quantum algorithm comes in. Suppose that using adiabatic preparation or some other knowledge, I can prepare a superposition of the ground state and some other, like first higher excited state, psi 1. I may not know epsilon, that's fine. But what I can do is to perform a quantum algorithm. This is essentially Shor's famous quantum factoring algorithm, rewritten and expressed in the form known today as quantum phase estimation. And it allows us, if we can perform a controlled evolution by time, some time t, evolution by time t squared, t to the 4th power, t to the 8th power, t to the 16th power, exponentially increasing amounts of time. If I can do that, and that's a very big if, and I perform a quantum phase Fourier transform on the phases that are kicked back into these single qubits. This bottom register is a full system. Each one of the top 3 lines is a single qubit. Then I should be able to measure this, and with some probability determined by epsilon, I will get the energy gap, or the ground state energy, and the ground state of the system or the excited state of the system. This is a beautiful, beautiful textbook construction. This is where the experimentalists would like to catch up to the theorists on. But there are some catches with that algorithm. It requires one to do these large controlled Hamiltonian evolutions by exponentially increasing times. It therefore is really totally unrealistic to realize. Thus, what theorists have come up with, and this is again another innovation, was this following idea called the variational quantum eigensolver. I know many of you in the audience, especially if you are from one of the companies or are using one of the corporate quantum computing systems, have been thinking or practicing this technique. It's very easy to understand. The basic principle is the Rayleigh-Ritz variational principle. Suppose I have a way to construct a quantum state that's parameterized by a classical vector theta. And then I can measure, let's say, expectation values of that theta and the Hamiltonian I wish to simulate. Well, no matter how I change theta, this expectation value can never be larger than the ground state energy. So I'm free to wobble around this theta, wobble it intelligently or not as you desire, until you get the smallest value you can get, and you can call that an approximation to the ground state energy. Voila, really simple. It's hard to go wrong, because you might even have crappy hardware, and then you can say you still can't get lower energy than the ground state energy. So what do? You prepare an initial parameterized set of hardware components that may have 1 qubit and 2 qubit component constructions. You measure the expectation value of the energy. You then estimate the gradient in a direction. Which way should I change each of these thetas in such a way that it reduces the total energy, in principle? You feed that back after doing a classical computation into the quantum system and repeat, and do this over and over. And you invoke the gods of machine learning and optimization and say, this should be useful. I hear laughter from the audience. It's a very quiet laughter. Because machine learning has similar problems to this whole field. By the way, I teach machine learning at MIT. And it is seriously popular and seriously useful, and seriously completely ahead of theory. There are no proofs that machine learning should work in the majority of the cases. There's no proof that this should work either in the majority of cases. In fact, what is the cost of this algorithm? If you repeat, it turns out that the error you get largely requires you to do, if you want epsilon as the error in the output, 1/epsilon squared number of tries. Is that efficient? Those of you who are computer scientists? No. Really, we would want it to be polylog 1/epsilon, but it is not. This is statistical sampling. And so it is widely acknowledged, at least among quantum theory folks, that this is an exponential time algorithm. But we don't know. It's just like recognizing faces. It seems like that's a problem which should also be really hard. But there's some intrinsic simplicity to faces, because most of you don't have 2 noses or 3 eyes. And so there's an underlying pattern to it, just like there might be an underlying pattern to most Hamiltonians that are being actually simulated to perhaps allow this to actually work. But we haven't been able to prove it. This is where theory actually has to catch up with something. Okay. But a comment about this. One of the reasons why this might appear might be because it's very hard to estimate the gradient, which direction to shift theta in. We, in machine learning, build a great deal on the fact that backpropagation is easy to do, since you can get an analytic expression for the gradient due to the construction of the neural networks. So, yes, please.
Can you, when you say the cost is 1/epsilon squared, is that a theorem or is that an observation or what is it?
It's an estimate based on a huge number of approximations. So there's no tight lower bound I can give you for that. Yeah. That's another problem.
But is it possible that this only holds for very simple Hamiltonians, or that, and very small systems, and that once you start scaling, this won't really hold at all?
But it's possible that it may be much worse than this. And it's actually, yes. it's very likely that something like this will happen for random Hamiltonians of a reasonably local size. But you're not nodding for that one.
I would think of 1 over epsilon squared as a very good, this would be a very optimistic kind of result to hope for, and I wouldn't really criticize it that much. And
no, thank you.
I was actually sure that this was true.
For those of you who are listening remotely, this is Umesh Vazirani giving me a lecture about the fact that actually I've left out a very important variable here. I didn't put n in this. That's the really crux of the problem. And the scaling with epsilon may be less controversial if we just think of n. And n is going to be an enormous cost, probably.
Right.
Yeah. Okay. I have no idea what that cost will probably be. But as far as we know now, that scaling is not going to be linear. It's very likely to be an exponential n. So VQE has very, very poor fundamentals as its underlying assumption. 2 questions, one here.
Do you have to worry about being paranoid about local traps? Like, so you got this number, but is there a number that's smaller somewhere?
The question is, do you have to be paranoid about local traps? Absolutely, because there are no convergence theorems for this yet. And I'll show in a moment that at least you can get by one of the problems in principle. That is, if you're estimating the gradient discretely, like you're doing here, where you have to take 2 sets of thetas, take their finite difference, and then get the gradient, that leaves you open to many kinds of instabilities and local minima. Second question.
Won't the gradient be 0 at any eigenvector?
If you're so lucky as to get an eigenvector, I wish you much better things.
Arbitrary energy.
Usually you're not so lucky, because that's a set of measure 0 in this whole space. Yes, please.
Can you expand on your statement about scaling with n? Because the practical version of EQ would say you use a constant depth circuit, right?
Okay.
But you must be going beyond that.
The question is, can I expand on my elaborations about scaling with n? N here would be the parameter I would use for the size of the Hamiltonian, not the size of the circuit. And so that's the main difference. The goal, after all, is to simulate a Hamiltonian of some description length, n. Of course, if I just have a finite number of circuit elements here, that the scaling will go something like the number of circuit elements. But that's not what I'm concerned about. Yes, please.
N is number of local terms, not number of qubits.
For example, yeah. And the 2 may diverge very wildly. The question was, n is the number of local terms, not the number of qubits. That is correct. Okay, so I'll show you one thing about this that I find remarkable. Remember, this is a complicated circuit. Where is some intuition about this? Well, one of the neat things that has been observed is that you can measure the gradient dE d theta instead of having to measure at 2 points at infinite difference. And here's an example. So suppose I have in this construction, and this is taken from that review article I cite, a particular Hamiltonian such that the expectation value is given by this, a rotation about x, a y, and an x. And this may be a poly y that appears inside a local Hamiltonian term. Well, it turns out this circuit, which has 2 qubits, a qubit, which you're going to push phases back onto, and then the physical system you're evolving, will give you as an estimate, over here the measurement result will be the derivative that you were looking for. And it's not conceptually hard to see why. Because you have the evolution of 2 phase paths here. One when the qubit up here is a 0, and one when the qubit is a 1. In the case when it's a 0, the x and y do not happen. In the case when it's a 1, the x and the y happen. And this x here interferes those 2 parallel quantum pathways. And the interference gives you the difference between 2 phases. And that's why you get a gradient over here. But we know this kickback of phases and the interference of phases can be used for much more than just getting a gradient. But, people have generalized. And because you can now have a very large system here, kick back and measure a gradient, and this is a construction for a large Hamiltonian, not just a simple one I gave you a moment ago, this is now a recurring theme in the discussion, the world of thinking about these things, this world, not just for variational quantum eigensolving, but variational quantum circuits. And although many people don't say it so loudly, maybe variational quantum machine learning of some kind of sorts. Yes, please.
But there is a very big difference in the sense that each circuit only gives you one entry of the gradient instead of backpropagation get everything.
Beautifully said. The observation is there's a big difference. Each circuit only gives you one sample point of this gradient, not the floating point value of the gradient.
Oh, but also in terms of component-wise, I mean, this only gets theta j, but you also want theta 1 all the way to your theta.
Absolutely right. So I've left something important out here. There's in fact, this is my next statement here. There's a very strong assumption here that the measurement observable, that the Hamiltonian be of a very restricted form, in particular a sum of Paulis, and this is only giving you the gradient for one of those Pauli directions. So this is not at all equivalent to the kind of loss function feedback we have and we traditionally use in machine learning today, despite this hope that you might connect here. Okay, still, remember this circuit. We've seen this kind of circuit appear over and over again today. And the thing that we might want to also understand, because this is the other circuit that I've shown, this is quantum phase estimation, is that there is an intimate relationship here too. Suppose I kind of gray out most of the circuit. So here's the full quantum phase estimation. But let's say I only do this part of it, and there's one control qubit. Then this piece right here with this inverse QFT is actually the circuit that we've been looking at over and over again. This is known as iterative quantum phase estimation, Kitayev's algorithm for phase estimation. It appears in the book I wrote with Michael Nielsen as an exercise in that chapter. And the idea is that if you feed back, after you do this measurement, feed back to change this rotation angle to make it the optimal one, then out will pop the Fourier transform, the quantum Fourier transform. So, of course, in phase estimation, to make this efficient with the error, Pauli log 1 over epsilon, you must be able to do powers of this u efficiently. But even when you can't, you can run this and use it. And one article has come out recently, which I really liked, which showed that if you use that circuit, now stick it in your variational quantum eigensolver. So each one of these blocks is now that last circuit I showed, a Kitaev phase estimation. But then you use it as the parametrized circuit with all the thetas in your VQE, you get something which evolves all the way between the cost of VQE, that goes as 1 over epsilon squared, to the cost using phase estimation, which is 1 over epsilon. And you can vary that by the parameters that these authors use. So now we have this bridge that's growing between these kinds of approaches. And this has all been driven by the quest to look at ground state energies instead of the quest to do the full Hamiltonian simulation. So let me wrap up now. I have 3 slides to show you about how this is now driving a shift from thinking about these ideal cases into matching with reality. Because reality in the goals that you want to achieve, and reality in terms of what hardware is actually available, is actually very different. For example, real physical systems are actually bosons and fermions. And as I mentioned, fermions need global anti-symmetrization. So how do you map this onto qubits? Well, there are ways that are well known. One of the earliest was by Abrams and Lloyd. And the idea is that you take these wave functions which are in real space. They have very complicated potential matrix elements when you do this. But you can symmetrize these by putting them through a circuit, which is essentially a sorting circuit. And Barry and company made an exponential improvement between the original version and the current one that we know. This is in what is known as first quantization simulations. But another technique is in second quantization, where you use an operator algebra. And there, a very beautiful result was given by Bravi and Kitaev, which show how you create mappings between these fermion operators and qubits so you can get something which is a little more efficient to simulate. But I submit that this doesn't quite answer what we really need. These slides are 3 challenges to the field. That is, what we actually need is not just fermions or bosons. Bosons are the vibrational modes of molecules. They determine all sorts of whether something will be able to happen or not in reaction. We need a way to map combinations of bosons and fermions together onto qubits, not just one or the other. And so here are two ideas. We need to be able to work in states of definite symmetry. And there's a known quantum algorithm for this, known as the quantum Schur transform, after the Schur-Weil duality. And that allows you to transform wave functions like this into states of total anti-symmetrization, as well as all the mixed states of symmetrization in the Young tableau. Another possibility is that we might think of fermionic quantum computers, just like we now today have bosonic quantum computers. I helped a group at Yale go through a demonstration of a use of a bosonic superconducting quantum computer to simulate Frank Condon factors in molecules. But we could do a mixture of fermions and bosons, or maybe even fermions. But this is a conceptually interesting question. Okay. Second challenge of reality. Real physical systems actually have symmetries and utilize frames of reference. Like if I'm an NMR spin, I don't just analyze what's happening in the frame of reference of the lab. I analyze what's happening in the frame of reference of the qubit or of the RF frequency that's coming in. And this allows me to completely change the energy scales of the evolution. Things slow down if I move into the right frame of reference. How can we utilize that fact in the face of things like the no fast forwarding theorem, which says that quantum simulations cannot go any faster than the time scale of actual physical simulation you're performing? Well, it actually turns out there is now work on symmetry adapted basis functions, as well as fast forwarding for certain particular Hamiltonians. And I highly recommend this article to you. This is by Atiya and Dorit Aharonov, which show in 2017 that for some Hamiltonians, such as a quadratic fermionic Hamiltonian, you can get fast forwarding. You can evolve faster than the timescale of the simulation, significantly faster. It is not at all surprising because, for example, if you have a harmonic oscillator, you know the answer to the evolution. You can evolve as fast as you want because you have an analytical solution to the system. Now, if you have a harmonic oscillator that's perturbed a little bit, how do you combine that with your known analytical solutions to be able to speed up the solution of that system? Now, that's a hard question. And if you have that perturbation and you have a symmetry, for example, maybe you could use an interaction picture. And this is a beautiful result by Guanghao Lo and Nathan Weeb about how you move into the interaction picture. But I submit these two need to be put together. What we need is both symmetry adapted and fast forwarding to give some kind of new picture for evolution. Not interaction picture evolution, but fast forward picture evolution and symmetry adapted picture evolution. We have a fundamental theory challenge here. So that's challenge number 2. Challenge number 3 comes from the fact that real physical systems have really many, many quantum classical boundaries. And this is the heart of why we simulate things very efficiently, in many cases using classical supercomputers. And thus, it is known that open quantum systems are key to many of the properties that people desire from these simulations and experiments, particularly because they are not cold systems. They're systems at thermal equilibrium, sometimes a very high temperature. After all, you are not living in a vacuum at 0 temperature. You're living at 20-some degrees Celsius, and your molecules are vibrating wildly in a water bath. And this is not what a quantum computer is seeking to simulate today, but that's reality. How do we simulate such realistic systems? Well, there are some beautiful advances. I like this result from Garnick Chan's group, known as quantum imaginary time evolution. There's work on a technique known as quantum embedding by a variety of groups. And I commend this to you. I don't know if Andras Guillen is in the audience. And I think this result is perhaps the most important result in quantum algorithms that has come out in the last decade. It is a result that shows how one can transform I showed you before this quantum signal processing transformation of a Hamiltonian. This result shows how you can modify and measure the singular values of an embedded operator, like a Hamiltonian, or even another different kind of operator. Singular values, not eigenvalues. Singular values are things that tell you about the principal components of something. It's extremely important in making approximations to know what is the important part of a system. And if you can transform those by arbitrary polynomials, you have a remarkably powerful tool for doing things like measuring statistical and thermal properties. This is an algorithm which essentially moves and connects all the way between Grover's algorithm and Shor's algorithm with a single algorithm and a parameter that varies between the two. I've been calling this the grand unification of quantum algorithms. And the idea that I have for this is maybe we should build on these techniques and find ways of doing quantum simulation algorithms that work with semi-group operators, not unitary operators. And that maybe we can find ways of getting statistics from these singular values rather than focusing on eigenvalues. So I hope I've shared with you something that's interesting to you. I started with evolving time, talking about ground states and shifting reality. But overall, I hope I've shared with you something about the majesty of SU2. Remember, we started with this quantum walk that said qubit left, qubit right. And it was this two-like system thing, a qubit plus a system, a large system. We then moved into linear combination of unitaries, same thing, a qubit plus a large system. We then looked at quantum signal processing, a qubit controlling a large system. We then looked at gradients for variational circuits, a qubit and a large system with phase kickback and some transform at each kind of these steps. And in iterative quantum phase estimation, Kitaev's algorithm, exactly the same structure. There is something going on here. There's something we need to understand. This is something like quantum singular value transformations. But there's something that unifies all of these. And that, I think, is the majesty of SU2. And I hope you'll join me in bowing in reverence to the qubit, which has made all of this possible. Thank you.
Questions?
In the adiabatic slide that you showed sometime earlier, you mentioned the slow evolution. Is the S the time there?
So the question is, in the adiabatic evolution, is S the time there? S turns out to be an artificial time, which is going to be my control time of evolving between the starting Hamiltonian and the problem Hamiltonian. So therefore, I can dial it with any kind of schedule of change. It can be linear, it can be sudden, it can slow down where I think there might be a problem, and so forth. Effective time. Yes, please.
For this technique about the quantum signal processing where you want some Hamiltonian that's encoded in a unitary, did that intuition come from the fact that the linear combination of unitaries was easier to simulate, or why, I don't know, that structure, or what's the intuition behind that?
The question is, what is the intuition behind the embedding of the Hamiltonian or other operator in a construction like quantum signal processing? Did that come from the linear combination of unitaries? It really came from Guanghao Lo, and somehow it just popped out of his head. And if I may guess, I think that some of it was inspired by linear combination of unitaries, but for me, it really was inspired from Grover's algorithm. Grover's algorithm embeds the concept of how do you get composite pulses on multiple qubits by showing this thing of block encoding a unitary in some other qubitized system. So we came up with the concept of qubitization motivated by that. But then it was Guillen and Nathan Weeb and company with Guanghao Lo who then figured out, and Yan Su, who then figured out the right way to actually analyze that. So there's more to it. And many things actually in physics are embedded in this way. If a photon scatters off the wall of an optical fiber, it's really kind of controlled, its phase is controlled and kicked back by the behavior of the wall, which is a very large physical system. So maybe that physical system doesn't have to be unitarily evolving, all sorts of things. But we need a unitary description of what has happened. That leads you to a block encoding. So that's why there's an intimate relationship between this and maybe open quantum system dynamics. Yes, please.
You mentioned on one of the slides Childs' new algorithm called it Trotterization 2.
I called it Trotterization 2. He did not.
Does that use a similar structure? Does that use Ancilla at all? Does the original?
Great. The question is, in Andrew Child's team's recent January 10th preprint, where he analyzes trotterization and error, does it use the same idea, for example, as quantum signal processing? The answer is no. He does not need to rely at all on quantum signal processing ideas. But it is my assertion, with no proof, that underlying this is exactly the same physics. That it is really just SU2. How do you walk on a sphere and have things happen? And trotterization is a way, just like Solovay-Kitaev, of walking around a sphere and having certain errors that you do not desire cancel out. And that is exactly also what happens in quantum signal processing, but somehow we've arrived at these results via very different intuitions. Somebody needs to grand unify all of those ideas.
Thank you. It's a great talk.